Okay, so welcome to the Automotive Work Group update session. I just used the last 30 minutes break to add a few more slides. I saw we've discussed a lot about the STPA. To not really explain what STPA stands for, so for all newcomers, I put in 3 slides to just give a very rough idea on what it could mean. Overall, I don't want to focus completely on the STPA analysis alone, but I also would like to say why we did this and what will come next, what is important, and also how this telltale use case can act maybe as example for other use cases in the field of automotive. I had very good support overall in the Automotive Work Group from many contributors. Also now for the slide set there, I took the liberty to take some of the slides from Paul, and also Christopher was giving good guidance on during the STPA analysis with all his background knowledge on how telltales are implemented in practice. So thanks a lot to both of them for the great support, also creating the material. And as in the welcome session, there was limited time to just say what we are and what the different work groups do. So basically what we set as a goal for the Automotive Work Group is that we discuss the condition and prerequisites which the automotive sector needs to integrate Linux and safety critical system. And it's most likely the no-brainer because it's the Automotive Working Group. And what we try to use actual use cases from automotive domain and to derive then the technical requirements to the kernel and the development process around this. Some part of the process we also put to other working groups, so there's interaction with the OSAP and architecture around this. And our activities nevertheless are documentation. We figured out that there's a lot of work going on in automotive, but not everything is visible. And independent which operating system you consider to take, we said we need to get a lot of documentation later on. This also helps in onboarding new members which come into the project. And by this, we write down requirements, system architecture, have an item definition. And but we didn't want to have just theory. So basically, before we actually documented, we already had some reference implementation. See, there's the incomplete sentence in there. The reference implementation illustrating the use case in something which you can download and experience, similar also like the idea from the systems work group. Then whenever you do something on the one side, you need to iterate back to the other one. So it's not that you really live in a V model where you just first document, get to implementation, going up and you're done. Everybody knows it's a lot of increments in there. And therefore we iterate and get forth and back. We also reached out to other communities like AutoSAR and hope to also increase this interaction with further communities. From the session today, I'll explain first upon what a telltale is and why it's the use case for the Automotive Work Group, where the benefits are, and then how we approach these use case thoughts for telltale with using the system theoretic process analysis. And there I added a few slides to explain what it means. I assume some of them will be more help for the automotive guys. For those who are not automotive, I guess there was also the good idea, short explanation from Paul saying that this can be applied also not only to safety critical application, but you can also use it for business cases or saving costs or customer experience. It's really a wide approach, which can be used in many use cases, but we use it here for our analysis of system architecture to derive requirements. Later on, more on this. And of course, there is some next steps and outlook to what we are doing, how we continue, and how this use case can be used as derivative work for further use cases. So why telltales? I guess almost everybody knows what a telltale is, but you don't know what the main stands for. Actually, a telltale is just a simple warning sign and giving safety sensitive information to the driver via the display or the instrument cluster or dashboard, however you call it. Recent days, these former mechanical dashboards with physical light bulbs turned into first LED, and now that we have full display solution. And there you can see the rendering icons like check engine, what gear you're currently in. So on this picture, you can see here it's the number 7. So this is some safety critical information that you're getting informed which gear you currently are. If something is not working properly, like oil pressure, this is all telltales. And we basically took this use case to have as a backdrop to drive our safety requirements, what we put to the kernel. And the nice thing about the warning signs is that they don't involve complex sensor actuator setups, right? So it's really something you can experience, you can simply explain, and well, it's still complex enough, but relatively easy to understand. And this showed the basic challenges which you have in the system, and they are representative for more complex use cases. So that's just telltale. You're wondering maybe why we don't took the driver assistance or so as a starting use case, because this is where the momentum currently goes. But we said in the first shot, we'll go more on the use case, easy to transport to others, and as I said, having less interaction with sensor actuators, a lot of different system architectures and so on. So I'll later on show anyway the evolution there. Right. It's nice that in this use case, we have just fewer subsystem components compared to the driver assistance use case, right? Also drawing system architectures, you have a lot of chances to draw this for driving a system, but here we can fast argue that this could be a reference architecture, system architecture. It's nice to visualize. I just had this one picture, could show you the display and say, here's the gear, that's the point in there. And it also typically has a moderate safety integrity level. So it's typically set as ASIL A or B. What's really wonderful is the relaxed timing constraints, because otherwise we would have a lot of discussion about real time directly. But here we go that something is displayed on the screen. And I guess everybody who has been in a bicycle, motorbike, or in the car and saw a warning sign, it's not that you directly stop, turn right, and check first what the instruction said. Typically drive forward and say, okay, here's something not going on well, so I take the next stop, go outside. So the reaction on what you see already takes longer, and also the processing and really things around it. So therefore, we have long reaction times and have also, a fairly nice high-level system diagram. It's coming on the next, or no longer next slide, it's coming on a few more slides due to the inserting of the STPA. Another nice benefit is that there were sample implementations available. We worked together with the automotive grade Linux here. They had already an instrument cluster, and we put our little safety monitor app in there. That's basically how we started. And Qt-based applications, so not considering safety there, but to understand just and illustrate something. There's one of the first workshops where you can really see the demo based on QEMO as well, because this is easy portable and showable, and everybody can reproduce at home. Which also gives the drawback that there is no physical watchdog in there. The watchdog importance I will explain later. And well, and as I said also before, we have the possibility to scale to different hardware software architectures, increase safety demands of the kernel step by step, so we can start small, think big, similar like for the systems work group. So, but now we have selected this use case. We see the benefits of the telltale, and it's time to approach its use case. So we had a lot of forth and back, many discussions. Sometimes we took good notes, sometimes less good notes. We got new people and they came up questions, and we said we need to be a little more structured and have a good guidance around this. And the system theoretic process analysis act as a very good tool and methodology to get in there. So now STPA, if you don't know what it stands for, it's the System Theoretic Process Analysis. For the automotive guys, with simple words, STPA can slightly be compared to HARA, so hazard analysis risk assessment. What I really like is, as you can see, they're diagrammed around this, and less big spreadsheets, which are typically done and involved are in a hazard analysis risk assessment. You can go to different levels and so on. And we have also a good slide set on this from Paul. I took the link from the last presentation, so from the workshop in April. And I really recommend also the handbook around this. I think the first page is a good part, and somewhere also in the end there are some examples on this. So it's a good read and not too many pages to get an idea. And maybe it also fits to other use cases which you have, like for security, business failure. So quoting here what Nancy Levinson has written in there, so it's relatively new technology and it's an external model of accident causation. And yeah, I guess the main thing I have already said. The good thing is it can also be put to system components, not to full system. You can have it on system elements which you're not aware of yet. And that's a nice part. So in summary, also very complex system can be analyzed with this methodology, but you need to be very careful. Also, Gab was mentioning that it's, if you take the Linux kernel as such, it could be very, very complex. So you need to see how you really go through it and how you make this, but it's made for this complex system, but you need the experience also and gain your own experience to get this in. Right, then it also helps to make more and more detailed design decisions. You can start on a higher level and go to a lower level. Provides then directly documentation of system functionality, which is very good. And what I like, you can easily integrate this into your own model-based or whatever system engineering process within your company. So this is just the STPA theory around this, so that you have heard the word and can connect a little bit to it. And yeah, so from the status, we had focus on the system theoretic process analysis, STPA, for getting better requirements to the system, the constraints, so also Gab was mentioning it. And we used this to identify important elements of the system, see which safety responsibility they get and what of this should go to Linux, what should be to other components. And this was really important because, as I said, we wanted to go directly deep dive into the kernel, and we left this level by intention because we couldn't see where to look first, what to really concentrate on, what is the critical path in this, how does it come all together. And therefore we put this on the system level and we iterated back on a second level of the system architecture, giving them more details, going onto unsafe control actions. But this is also something you could hear that we need to align stronger and will align stronger with the architecture work group, because a lot of our work is still OS independent. We're just in the process of diving into the OS dependent part. Right, and yeah, we now have the chance to put risk to different domains and units as set, where strengths, where limitations of Linux, and putting it all in a system context. We have telltales. Telltales are part of the system that include the instrument cluster. Someone would like to get some telltale request, it could be the engine or whatever. So this sends messages to the cluster itself, or to the system, including the instrument cluster. We have non-safety relevant parts. The speedometer often is not taken as safety critical, for example, because you easily can estimate if it shows 550 or 100 miles per hour, you will feel the difference and don't trust what's written there on the speedometer. But then we have a display definitely involved. The display shows our information and giving feedback to the driver of the vehicle that everything is in a good state. And to reduce the responsibility in the first shot, we're coming closer to an EGAS approach, where we say a strong involvement of an external watchdog can really monitor also that we're doing proper handling of telltales, and in case switch off the backlight. So this monitoring part, the feedback pass here, getting back information, is often called the backward pass. And forward and backward pass are really interesting elements, which I'll put on the next slide. Here, the way forward basically means what comes and gets rendered. So everything on the way to the display. But you need to make sure that what's ever on the display is getting back. So for this part, you need to see that the display is proper and correct. And there can problems occur on the forward part, which would interrupt or disrupt the proper rendering. And so even there are libraries which claim they have safety qualifications. So there's one from Qt, which actually looks on safe rendering. And but it's still the forward pass, and it just covers one bit of it. And in the end, you need to make sure that whatever ends up in the memory will end up also on the screen. So you will have a checking mechanism. So whenever something goes wrong in the forward pass, there is your fallback and your proper checking in the backward pass. So, and yeah, even if we rely on an external watchdog, this is just our safety net. In theory, it should never be triggered and everything should be properly theirs. And there's a lot of responsibility to Linux anyway. We need to have a good timing in there, that things come in place, that's reliable, robust, stable, dependable, everything which you also have these days from servers, but well, for safety, there's a bit more. And as said, so really as a conclusion on the slides, the system is considered in a way that the watchdog is never triggered during a safe state. Yeah, you saw the high-level diagram here and this forward-backward pass. If we look into the control structure, this gets a little more crowded overall. There are these gray elements which are considered outside the direct system. So we mainly concentrate on the bluish and white boxes. One element is that you can see there is a read-back interface, and this read currently goes to the frame buffer. This is something which will not happen in real part because we're starting our display checks from the display controller side. So there's no direct connection here, but this is actually part of the backward pass. Even the display itself needs to have some checking mechanism. So we have the full pass in here, which is going back up. And we made the simplification, so we're not sure how it ends up in the end. This is the iterative part. So how we implement for now, it's basically that this readback interface will read information which is in there in memory in the frame buffer. But of course, things happen afterwards, so it should be in another way. You see how we end up there. So this is where I said here it will break with the example implementation. Also, this analysis is currently detached from Linux as an operating system, which is causing the architecture work group a little bit of headache. But in this way, you can also transfer it to other parts. And we wouldn't have done all this if the information was provided, but long invest in search, it's hard to find a common sense. So we said better get our understanding there on the system and make it on our own. Some element which you cannot directly see here, which will give a very interesting part, is the timing constraints, because rendering, return buffer checking, display showing, they are all different, have other frequencies like 60 Hertz. Some parts may be rendered with 10 frames per second, other maybe even faster than there's request. So this is something which you cannot directly see in here. So the really dynamic behavior is not fully covered. Right, so then I'll come to which similarities this brings with other use cases. Basically, as we put things down, I made this a red warning here. It's really oversimplification, but if you see, we need to make sure that there is a memory region, a certain value in memory stored properly, and it's checked against another reference in storage, memory, wherever this is. And you need to make sure that these two are properly checked in a proper amount of time. And by this, we have some assumptions in there, and it's going closer to the safety element out of context argumentation from the ISO 26262 part 10. But here, very important remark, I always like to stress this, if it's meant as out of context, it's always in an assumed context. So it doesn't mean when we would have a working safety case for the telltale rendering that you can simply say, well, it's telltale rendering, it's Linux, and the Linux is now certified, so just take it for whatever use case you have. It's not as easy as that. But yeah, we use this use case to derive requirements to the Linux kernel and see what is in common also with other use cases. And for this, I would like to illustrate the similarity to some other use cases. We took this as said due to less complexity, but if you take, for example, a park distance control, which works with sensor, ultrasonic sensor, other sensors, you can have surround view camera maybe, and here there's some data sent, it goes into the system, it may be combined with audio part. Everybody knows that the audio is switched off when you put in the rear gear and you have the park distance control, which goes through the speaker rather than the display. Not sure how they put the safety part in there. Maybe not everywhere there's a safety integrity level assigned to this use case, because you anyway have to watch the mirrors and it should just be a audio support on it. Don't know, so just put a question mark in here. Didn't cover the use case too much in detail. And therefore, for surround view use case, for example, the camera, you actually have very similar elements, and you may put just some guiding lanes or so in there, doing some rendering on top. So you will make sure is the rendering properly done. So you come to a similar use case. Now, if you want to stick with the telltale use case, you can also consider how to make more responsibility to the kernel, like replacing external watchdog, which we explicitly considered as an internal watchdog, use inbuilt or make the control via Linux kernel. So there's freedom of choice, so you can take the work which we're doing and bring this forward into other use cases. So what we will do next is that we have now drawn a good diagram which looks different from the architecture workgroup, if you have followed this, and was already mentioned in the architecture workgroup that it's a quick shot and incomplete still. So we will start to bring this together and also see that we write down a little bit how the things are designed properly. Actually wanted to deep dive into an implementation part also, but we said if we now go just from this level to implementation, we should have a proper concept in between, explain others, and also be able to distribute tasks. Right. When we do this, we want to focus on what matters for safety. And I would like to stress this because it's the way how we're doing. And it's not that you have to do this in this way and that you, for any case, can do this in this way. So it's just a thing which is important for safety. And yeah, by this part, combining architecture workgroup, going really into which subsystems, Linux kernel elements are involved. We need to see where do we put things, are the unsafe control actions, are the constraints fulfilled, how do the requirements fit. And yeah, additional next steps, as said already, align with the architecture workgroup. This will be important. We'll reach out to the systems workgroup, so to see how this use case also fits into this architecture, how we can make use of it, how does our AGL implementation fits to the implementation of the systems workgroup where AGL should be involved. And we also would like to promote this use case because, well, if you hear telltale, first of all, you ask, what is a telltale? Then you say a warning sign for a cluster and say, well, how does it help me for my autonomous driving? And I guess this is the way forward. We need to really start this and say the starting point for additional use cases. You can put this into discussions and bring this forward. So I took one final slide before I conclude. You can see we have the telltales. You can consider park distance control, self-parking application, which have a certain responsibility already, where algorithms are rendered potentially on a Linux or their OS. And on a long run, there could be also the guides through autonomous driving, while we for now say, well, by taking the telltale use case, we are on a good path and seeing which requirements are there for Linux, which could be next steps, what is in our scope, what's out of our scope, where to put certain elements. And by this, we hope we really give a guide also for other communities, other projects, other companies for their use case. And I assume there will be a lot of use cases around which can benefit even from a telltale, which doesn't look like the new fancy thing, which currently everybody jumps on like self-parking or autonomous driving in print. So, okay, that's it. Thank you for listening. And as always, feel free to ask questions, reach out to us, join our calls taking place Wednesdays, subscribe to the mailing list, as we already have more than 150 participants in there. It's a good number. So yeah, thanks a lot. 5 minutes left for questions.
Any questions?